For this lesson, we will go over Poisson's ratio. Let's look at some of the learning outcomes. We want to understand and define Poisson's ratio and calculate Poisson's ratio using the formula nu is equal to the negative strain lateral over strain longitudinal. When a loaded bar is in tension, the axial elongation is accompanied by lateral contraction. Consider a deformable body subjected to an axial force, tension. The body elongates, which creates normal stress and strain. In this diagram, L is the original axial length, while L' is the elongated length. D is the original lateral length, and D' is the contracted length. Now we can define these two formulas where longitudinal strain is equal to the difference in longitudinal lengths over L, and lateral strain is the difference in lateral lengths over the radius. Within the elastic range, the ratio of longitudinal strain to lateral strain is constant, which is Poisson's ratio. Poisson's ratio is equal to the negative lateral strain over longitudinal strain, and this is dimensionless, depends on the material, and is in between 0 to 0.5. In the diagram, longitudinal strain is equal to L' minus L over L, and lateral strain is equal to D' minus D over radius. Let's take a look at this example. A hollow plastic circular pipe with length LP, inner diameter D1, and outer diameter D2 is inserted as a liner inside a cast iron pipe with length LC, inner diameter D3, and outer diameter D4. Derive a formula for the required initial length LP of the plastic pipe so that when it is compressed by some force P, the final length of both pipes is the same, and also at the same time the final outer diameter of the plastic pipe is equal to the inner diameter of the cast iron pipe. First, to find the lateral strain for the plastic pipe, we have to subtract D2 from D3 and divide by D2, as the compression causes the gap between the plastic pipe and the cast iron pipe to close. Poisson's ratio is equal to the negative lateral strain over longitudinal strain, which we can rearrange for longitudinal strain. Longitudinal strain is also equal to the deformed length minus the original length over the original length, and we can rewrite this as LC over LP minus 1. Now, since both of these equations are equal to longitudinal strain, we can make them equal to each other. Rearranging for LP, we get the following formula, where LC is divided by 1 minus D3 minus D2 over VP multiplied by D2. Using the following values, find the initial length LP and the final thickness TP for the plastic pipe. First, we want to substitute all the values into the formula we got previously. We get an initial length of 0.2514 meters. Next, we will find the change in thickness by rearranging the lateral strain equation. This is equal to the lateral strain multiplied by the initial thickness. To find the initial thickness, we take the difference in diameters and divide it by 2, since there are two pipes. This gives us an initial thickness of 0.1 millimeters. To find lateral strain, we subtract D2 from D3 and divide by D2. This gives us a value of 1.818 times 10 to the negative 3. Now we can find the change in thickness, which is 1.818 times 10 to the negative 4 millimeters. Lastly, to find the final thickness, we will add the initial thickness with the change in thickness, which gives us an answer of 0.10018 millimeters. Using Poisson's ratio, we were able to find the initial length, which was 0.2514 meters, as well as the final thickness for the plastic pipe, which was 0.10018 millimeters.